Who's down to test the difference between two variances or two standard deviations? Hello, once again, this is Professor Grenfell's Math 12 Statistics class, and we are continuing today in Chapter 9. In 9-5, we're going to be testing the difference between two variances or two standard deviations. And what we're going to see here is yet another new distribution, and thus a new distribution table that we're going to have to utilize and learn to utilize. So here, let's actually see if I can do this. Let's do some graph paper. Look at that, wonderful. And as closely as I can, let's put in a y-axis and an x-axis here, kind of like this. And we'll go through some various characteristics of the F distribution. So first of all, it is a family of curves. There's one potential example. Here's another one. Here's another potential kind of graph. They all kind of look similar to the chi-squared distribution, but it's important to not get this this issue. Let's say it's important to not get this issue of comparing two standard deviations or two variances with the chi-squared test, which we would use when we had just a single specific variance or standard deviation value that we wanted to test. So here, the F distribution depends on degrees of freedom for the numerator, so df numerator, and also the denominator. So we'll refer to these, just for brevity's sake, as dfn and dfd. Degrees of freedom for the numerator and the degrees of freedom for the denominator. So the values of this distribution, notice we stop here at the y-axis, and there's nothing to the left of it. So there are no negative values. F cannot be negative because variances and standard deviations are always positive or equal to 0. The distribution is positively skewed. So notice all of these are kind of trailing off to the right. The mean of this is approximately equal to 1. All right, that's a fact, but not very interesting or useful. And then, again, like I had said, the F distribution is not just one single function. It is actually a family, a whole infinite set of different functions, different curves, that depend on these two degrees of freedom, the degrees of freedom from the numerator and the degrees of freedom for the denominator. So there are these two items, plus, of course, we also have alpha. So we're going to have to, the first thing that we're going to have to do is learn to utilize the distribution table for our F distribution. It's a little bit tricky, but once we get used to it, it will be fine. Oh, just one thing. I wanted to clarify the dfn, that n should be a capital numerator, and then dfd is not super important. I just wanted to make sure my notation was consistent with what it said in the book. Okay, let's get on into example 9-12. Here we're looking on page 529. So this example reads, find the critical value, so that's CV, for a right-tailed F-test when alpha equals 0.05, the degrees of freedom for the numerator, so DFN, are 15, and the degrees of freedom for the denominator, DFD, or 21. All right, so the first thing to do here is to take notice of this. Alpha equals 0.05, and it is a single-tailed test. It's a right-tailed test. So for us, that just means we're going to use 0.05 for alpha, DFN equals 15, and DFT equals 21. So here, this will illustrate how we use the F table. First, we'll locate it. So in our textbook, it is Table H, the F distribution. This is on A15, the 15th page of the appendices, or Appendix A, or it's on page 783. Then the next thing that we have to do, so you can see there's actually, this table extends across numerous pages. So we actually have to flip all the way to page 786. And that whole page of values corresponds to alpha equals 0.05. So here, page 786 is the whole page, nothing but alpha equals 5%. So notice there are three different things. All three of these underlined quantities, the yellow alpha, the green DFN, and DFT, these three values all have to be fed into this table. So we're starting by locating the correct alpha value that we're using. Okay? If it's a single-tailed test, a right-tailed test, then we're just going to take the alpha value that they give us. All right. Later we'll see if it is a two-tailed test, we have to use, instead of alpha, we have to use alpha over 2. All right, but let's just go through the mechanics of this. On page 786, alpha equals 0.05. We're going to go all the way on the left-hand side. That's talking about DFD. All right, so for DFD, we have 21, so we're going to go down to row 21. And then across the top, we have DFN. So we're going to locate the column that corresponds to 15 degrees of freedom for the numerator. And we're going to just go ahead and link those two together. We're going to see where row 21 and column 15 join up. And that gives us the critical value, 2.18. So this would be our critical F subscript alpha. Again, here I'll mention it. If the precise degrees of freedom are not found in our F table, we'll basically round down. We cannot assume more degrees of freedom than we actually have, but for example, if we need to use, let's just say for the sake of argument, if we need to say 27 degrees of freedom for the numerator, and we notice that it goes from 24 degrees of freedom all the way up to 30 degrees of freedom. Even though 27 would round to 30, if we followed proper rounding rules, that would be giving it 3 extra degrees of freedom that it does not have. So that's why we always round down. You can't see me, I'm doing air quotes, round down. We'll just take the maximum degrees of freedom that we have. And so if we have 27, we don't have 30, so we can't use 30. We would have to use 24. In that example, I'm just using those two or those figures as hypothetical values. All right, so that was pretty straightforward. Let's move really quickly to the next example. So here is example 9-13, located on page 530. It says to find the critical value for a two-tailed F test with alpha equals 0.05. When the sample size from which the variance for the numerator was obtained was 21, and the sample size from which the variance for the denominator was obtained was 12. Okay, so I've got all of that recorded. Now, what I had mentioned earlier, we have a two-tailed f-test, and so we're given this value for alpha, but whatever that is, we have to take that and divide it by 2. So for a two-tailed test, we have to use alpha divided by 2. Okay. I'll show you a little bit more about that in just a second. So for a two-tailed f-test, the F distribution curve is sketched in purple. It kind of looks similar to the chi-squared distribution. And I have shaded in the critical region. So here is the right side critical region over here, and here is the left side. Because of the nature of the test statistic that we use, these are always going to be a right-tailed test. We're always going to have an F statistic that is greater than 1. Remember, the average value for this distribution is approximately 1. So 1 is right here where the distribution is the tallest. All of our values are going to be greater than that. So we're going to just be looking at this critical F value. And this, since it is a two-tailed test, is F subscript alpha over 2. So that's why we have to use this particular alpha, or this significance level for this F test. When it's a two-tailed test, you take the alpha and cut it in half. That's the moral of that story. All right, let's move on to the DFN. So our sample for the degrees of freedom for the numerator one, that's going to be, let's see, 20. So we take, well, n minus 1. All right, the sample size for this was 21, so the degrees of freedom are 20. And then for DFD, similarly, this is going to be 11. All right, so now we have all three values to plug in, so to speak. All right, we're going to, first of all, plug in the alpha by locating the correct page. So the fact that we are going to be using alpha over 2 equals 0.025 makes us look on page 785, where alpha equals 0.025. Then, what do we have to do? DFN is equal to 20, so we have to be looking in column 20. Thankfully enough, there is exactly a column for 20 degrees of freedom, precise. And then DFD is equal to 11, so we're going to be just looking at where row 11 and column 20 intersect on the page corresponding to alpha equals 0.025. So you see, there it is. We've included all three of those elements in looking up the correct critical value. And so this F value that we get, F subscript, well, we'll say alpha over 2, is equal to, oh shoot, I lost it. Oh, there it is, found it again, 3.23. And so before I end this video, I'm going to just go ahead and say a few more things about the F test. So what we do in order to calculate the F statistic for the test is we just take the two variances and we divide one by the other. Okay. The book says don't pay attention to the subscripts. So actually, what I'm going to do is I'm going to get rid of those entirely and say it like this: S subscript big squared. Remember, S squared is the variance. S is just the standard deviation. And here, S squared small is going to be the one in the denominator. So here, as the subscripts now suggest, whichever variance is greater, whichever standard deviation, and therefore whichever variance is greater, is going to go in the numerator, regardless of the sample size, regardless of which population the larger variance corresponds to. We're going to put the larger value in the numerator and then the smaller value in the denominator. Larger value of S squared, right? and this is the smaller value of S squared. So the next thing that we have to think about is this. For a two-tailed test, we're going to have to use alpha over 2, and we're going to make sure to graph it. On our graph, we're going to place the critical value. That's what our CV, that's what CV is, critical value, on the right side of the distribution. If it is a left-tailed test, for instance, if we want to say the variance of this population is less than the variance of this population, okay, when we're talking about the alternative or the research hypothesis, if this would be a left-tailed test, and so what we'll do, since we're going to be placing the larger variance in the numerator and the smaller variance in the denominator anyway, it's going to be fine to just go ahead and switch these around and say sigma 2 squared is greater than sigma 1 squared. All right, and then that way we turn it into a right-tailed test. So whenever we do an F test, our statistic, well, it has to be positive, but it's going to be greater than 1 because we're dividing a bigger number by a smaller number. And so therefore, we always have to set it up as a right-tailed test. Okay, even if it's a two-tailed test, we'll put the critical value on the right side and we'll use alpha over 2. If it is a left-tailed test, we'll just switch it around and make it into a right-tailed test. So it's always going to be a right-tailed test. Thing number 3, there's a lot to write. If you have standard deviations, so remember that is S, the standard deviation for a sample is S, instead of variances, remember those are S squared, then they need to be squared, right, in order to compute the F statistic, the test statistic, right? So don't forget that. And then the last thing, number 4, sorry, I paused it, is that we need to round down. So yes, to be clear, when the specific degrees of freedom that you're looking for isn't in the table, then use the closest value on the smaller side. So that's what I was mentioning, I think a little ways ago. We were talking about the degrees of freedom for the numerator, and I noticed that there was a column for 24 and then a column for 30. And I said, well, what if we had 27 degrees of freedom? Well, we would say that is not in the table. So we're going to use the closest value, but on the smaller side. So we'll say, yeah, it's equidistant between 24 and 30, but we're going to use the one on the smaller side. So we would use 24. So yeah, just to illustrate that, 24, 30, okay, for our degrees of freedom for I don't know, let's say the numerator is 27, right? Which one do we choose? We are going to go to 24 rather than 30. So that one's in red, and just cross it out. Okay, and then we'll get into a hypothesis test in our next video using the F test.